everyone, thank y'all for making our second anniversary. We have managed to exist for 2 full years now as Tap Talks. Usually, of course, we would do this in a large brewery and you get to talk with us in person, but with the current situation, we are doing things virtually. So I appreciate y'all still attending. I appreciate y'all giving your feedbacks and participating on all the ways possible. So today we currently have 2 paleontologists. We did have on the flyer there was going to be a third one, but there's been a family emergency. So Dr. Marilyn Nestle may or may not make it. If he doesn't, then best of wishes for his family and hope everything turns out okay. But on top of that, we do have I believe, Hillary, you are a vertebrate paleontologist, is that correct?
Yes, that is correct.
And then we have Dr. Bonnie Jacobs, who is also a paleobotanist, which I didn't even know was a thing. So hopefully they will both kind of explain some of the differences in that. And I'll have them introduce themselves. Bonnie, if you don't mind going first, can you tell us a little bit about what you do and what exactly is a paleobotanist as well?
Aha. Okay, well, I'm a professor at Southern Methodist University. I'm in the Department of Earth Sciences, the Roy M. Huffington Department of Earth Sciences. And a paleobotanist is somebody who studies all and any kinds of and parts of plants as fossils. So, you can study fossil pollen going back millions of years. You can study leaves. You can study tree trunks or what have you. Any kind of plant or plant part that can become a fossil would be studied by a paleobotanist. And just to remind you, I know that this is ancient history now, really, like even in the modern day ancient history, and that is that in Jurassic Park, the original Jurassic Park, Laura Dern was playing the role of a paleobotanist. You probably didn't even remember that, or maybe you do know that, but but what she did was mostly try and fight off dinosaurs and reach her hand in and pull stuff out of dinosaur dung, and I don't really do that, so yeah.
All right, Hillary, would you talk a little bit? So Hillary is from the Perot Museum, not the same as working at a university. So could you also tell a little bit difference of working at a museum versus a university?
Absolutely. So my name is Hillary Supers McLean, and my official title at the Perot Museum of Nature and Science is actually the Fossil Prep Lab Manager. So I'm a vertebrate paleontologist, but I'm also a fossil technician or a fossil preparator. And so working at the Perot Museum, we of course work very closely with SMU. We work very closely with Bonnie and her husband Lou Jacobs there, but we don't necessarily, we are here for the public. We are here to promote the science to museum visitors, to visiting researchers. There is a lot of overlap with academic universities as far as the science goes, but universities tend to have educational classes, tend to take on students, are a place of learning, a place of academia. And although museums promote learning, we are more for just general public education. I'm not a professor, I don't teach any classes, nothing like that. So I think that's one of the main differences.
Awesome. All right, so we will do a panel discussion after Hillary's talk. But feel free to ask all your questions in the live chat in the YouTube. It's on the right-hand side of the video. And we will collect those questions. And then after the talk, we will have panel discussions. We will answer all the questions. And I hope you'll have a lot of fun. So Hillary, whenever you're ready, if you want to share your slides.
I'm excited. Let's get started. So let's make sure I share the correct screen with everybody.
That's perfect.
Does that look good?
It does. You want to go to full screen?
Yes, ma'am. How are we going? Everyone good?
It's absolutely perfect.
Yes. Okay, wonderful. Well, thank you again. I want to reiterate, thank you so much, everyone that's watching and participating, for being here tonight. I'm really excited to be invited back to speak about something that I'm extremely passionate about, of course, dinosaurs. And so tonight, my title of my talk, of course, is No Dad, T-Rex Did Not Fight Stegosaurus, Pop Culture and the Rights and Wrongs About Paleontology. So before we dive into the lecture, just to start, I want to go ahead and introduce to you the person that kind of inspired this talk, of course. This is my father, Paul McLean. And he is a Google software engineer. He is a loving father, I would like to say. He absolutely shreds the synthesizer to the most obscure European progressive rock songs, but overall, he's a pretty cool dude. Now, this being said, despite him being all of these wonderful things, whenever I see him, he does like to remind me that Hillary, T-Rex, and Stegosaurus. So T-Rex and Stegosaurus, they fought, right? They battled. He remembers this distinctly from his childhood. He pesters me with it every single time I see him, to the point of me rolling my eyes back into my skull. I want to run screaming from the house, and I want to make it very clear to my father and everyone else that this did not happen. T-Rex and Stegosaurus did not fight, did not interact, never happened in the world. But I wanted to try and see, first of all, why he was thinking this, where this was coming from, and also examine a little bit further how pop culture continues to portray dinosaurs, and in some ways getting it right, but in a lot of ways getting it wrong. Now, just for my father, in case he's watching, but for everyone else, I did actually do a little bit of research, because again, he's adamant that he saw this in his childhood. And in fact, in the 1940s Disney film Fantasia, there is in fact a sequence where you do see a T-Rex and a Stegosaurus fighting. So subconsciously he must have picked that up. So I'm sure I can hear him shouting vindication from Denver, Colorado, where he currently lives. But continuing on, when my father was growing up, and what a lot of people growing up got used to seeing when it came to dinosaurs, was something very similar to this image right here. So we have, of course, your stereotypical lizard-like dinosaurs with tail dragging, cold-blooded, reptile-like, usually stupid, usually just bloodthirsty creatures. I must admit, I took the opportunity to include Captain Kirk in this because I absolutely cannot help myself. I'm not sure if a Gorn would be considered a dinosaur, but for the purposes of this talk, that's what I'm putting it as. And so this is something, again, leading into the rest of my talk, this idea of pop culture and the old versus the new. How is the science continuing to move forward, but where is Hollywood? Where is toys? Where is media? So before we get into it, again, a little bit of back history, and typically the science throughout the 1920s through into the 60s was agreeing with this image of these animals being slow and silly and stupid. However, in 1969, a massive paper hit the scientific realms. It was a paper published by John Ostrom with Yale University. It primarily has to deal with this dinosaur here, I always say it incorrectly, Dinocaeus. Everyone scream at me, forgive me, I'm not very good with this name. But what is very interesting with this particular paper was this image that was created by Dr. Bob Bacher, who some of you may be familiar with as the curator at the Houston Museum. And this particular image was incredible for the scientific realm. It showed this dinosaur for the first time as dynamic, showed it as fast moving, and showed it as warm-blooded. So again, animals that are capable of fast dynamic movement are not going to be your slow, steady, cold-blooded lizards. It also had a tail that was upright. It wasn't dragging on the ground. You can see that its limbs are elongated and almost bird-like, and it has a very bright, intelligent eyes. So from this moment on, the paleontological scientific realm begun what we call a dinosaur renaissance, where every paper that was published continued this idea of these animals becoming different and unique and interesting and incredible behaviors, incredible evolution. However, a lot of the pop culture still remained in this sort of realm. You didn't see a lot of that science transition to the pop culture realm until a I would say at the time, small film hit the theaters in 1992. And yes, of course, I'm talking about the bombshell that is the Jurassic Park franchise. And this is a film that I'm pretty sure you had to have been living under a rock to potentially miss. This is a film that was not only incredible for audience to see for the first time, but it also was incredible for the science. For the very first time, you saw dinosaurs on the silver screen as, again, dynamic, intelligent, fast-moving, hatching out of eggs, showing a lot of similarities with birds, moving in herds, all of that incredible stuff. And this particular movie had an incredible impact on pop culture, which we're going to examine. But I also want to just give some props to the other media that came out in the 90s that also continued to further the general population's view of dinosaurs. And of course, I'm sure most of you will recognize our upper left-hand picture, those being characters from Land Before Time, which, fun fact, was actually produced by Steven Spielberg as well. So he is, I would guess, a huge dinosaur fan, which I think is very fun. But in addition to the Land Before Time series, which I certainly grew up on, there was also an incredible BBC kind of wildlife documentary series called Walking with Dinosaurs, which again showed these animals as they lived. And then there was a wonderful renaissance in the art, especially with an artist called James Gurney, who is probably best known for his book series Dinotopia. However, all of these other franchises in the 90s didn't quite have as great of impact as the original Jurassic Park film. And so for the next part of my talk, I'm specifically going to focus in on the Jurassic Park franchise, and we're going to talk about it. Now, I'm not going to lie to you. I am probably going to destroy some hopes and dreams around this film. I'm sorry. That's just how life works. You just need to get over it and figure it out. But that being said, the Jurassic Park film did do a lot of things correctly for its time. Specifically, it updated a lot of these versions of these famous dinosaurs. So starting with one, this is Stegosaurus, which is one of my favorite dinosaurs. It is actually the state dinosaur of Colorado, where I'm originally from. So there you go, fun trivia fact for you. But traditionally, Stegosaurus had always been shown, like you see up on the upper left-hand corner. It had a dragging tail, it had a brain the size of a walnut, so it was stupid, it lived near marshes, all of these very unflattering images of Stegosaurus. And again, the Jurassic Park franchise did a really lovely job of updating the skeletal, making it correct. This, I believe, is a screenshot from the second film, where you got to see them again as these large, dynamic animals with a correct skeletal position. So really neat stuff. Additionally, they definitely upgraded Triceratops, which comes as no surprise since the main consultant paleontologist was a man named Jack Horner, whose favorite dinosaur is Triceratops, and he dug up thousands of Triceratops in his career. So I sure would hope that they would get this one right. And they definitely do. I mean, who can forget one of those very first scenes in the film of them around this sick Triceratops, of course, like Bonnie saying earlier, our wonderful paleobotanist character reaching into a huge steaming pile of dung to figure out what poisoned it. Really, really neat stuff. And I would definitely say that the Brachiosaurus probably got the best glow up, if you will, for the Jurassic Park franchise. Before Jurassic Park, sauropods were thought of by science, but also more so by pop culture, as only being able to exist within marshes and swamps and lakes. It was thought that they were just so big and so heavy they were not capable of being up on land, and in fact their long necks and noses up at the top of their heads acted like a snorkel. Well, again, the science moved forward. We realized that wasn't true. We found these sauropod bones in environments that were not lakes and marshes and swamps. And so therefore, the Jurassic Park film showed Brachiosaurus, a beautiful giant sauropod, walking across land, and it is just so incredible to this day. I will just say one of the greatest things that the Jurassic Park film ever gave us as a society, of course, is a wonderfully half-naked Jeff Goldblum. Thank you so much. I could stare at it for days. Yes. But let's go ahead and get into the real meat of this talk. This is what you're here for, right? The drama, the intrigue. This is what I wake up every morning and I shake my fist at Jurassic Park and say, why Jurassic Park? So the heinous crimes committed by Jurassic Park. Now, don't fret. I won't be jumping into destroying hopes and dreams immediately. I'm going to ease you into it. I'm going to make it easy on everybody. And we're going to start with this particular animal here. This animal, of course, is Gallimimus. I'm sure if you've seen the film, you remember it as running together, these ostrich-like creatures. You know, oh, they're flocking this way. I've seen this film a couple of times in my lifetime, that's for sure. But the main issue with this particular animal, I mean, they did a good job with the body, the skeleton's mostly correct, but what they mostly got wrong, and this will have consequences, of course, for other dinosaurs, is they left out the feathers. And I'm sure if you're a dinosaur fan like myself, you will have heard feathers, feathers, feathers beaten into your skull. I want to add it to a tattoo somewhere on my body. Why did they forget the feathers? And so the Gallimimus is one of these first dinosaurs that we know now. At the time we didn't, so I will give a little bit of credit where credit's due. But we know now we're actually fully feathered, and in fact looked a lot like ostriches. One of the ways that we know they were feathered is we can look at the skeleton of this animal, and there's actually remnants on the skeleton that does inform us that these were feathered. So even though we aren't necessarily finding the impressions of feathers along with these animals, by the way, this is a skeleton from the Royal Tyrrell Museum in Calgary, Canada. If you ever get the chance, it is an incredible museum. But if you look very closely at the forearm limb of this particular dinosaur, you'll see on here these unique structures, and this is actually a Velociraptor arm, so, you know, a little hidden hello for a little bit later in my talk. But Gallimimus and Ornithomimus has much the same structures. They have what's called barbs. And these barbs are bumps along the shaft of limb bones that would have been attachment points for long feathers. Maybe not necessarily flight feathers, but some sort of skin integument, some sort of feather. So we do know that Gallimimus were feathered. Now, moving on to another one of our heinous crimes, of course, is this very famous dinosaur here, Dilophosaurus. And who could forget how it raised its side frills and spat venom in the eyes of our unfortunate villain character as he was attempting to escape. But like with our Gallimimus, they definitely took a lot of liberties with this particular dinosaur. This is in fact what Dilophosaurus looked like. It is still pretty scary. It still has that head crest, but it doesn't have the side frills. And the reason we know it doesn't have the side frills is, one, there's no attachment on the skull for side frills, but additionally, if you look at animals today that have these frills, particularly in frilled lizards, they have these large frills in order to scare off predators. They are usually a smaller animal that is a prey item that uses their frill to intimidate and hopefully allow them to escape. Now, Dilophosaurus was the apex predator of its time, and so therefore it doesn't need to scare off any sort of creature. It doesn't need these things. It doesn't need to put the evolutionary energy into building a large frill. So when we look at modern day animals, we know there isn't any correlation. Additionally, the most famous defense technique of Dilophosaurus is, of course, the venom spitting. And we can look at modern day animals that spit venoms. In particular, snakes are some of the most famous ones. And if we look at snakes, we actually see that built into their very skulls is an area for a venom sac and muscle attachment to actually help them spit that venom and generate that venom. But when we compare it to the skull of a Dilophosaurus, we do not see that area. We do not see those muscle attachment points. We do not see that area where there might have been a venom sac. And there's also no area for that venom to escape. So again, this was pretty much completely made up by the Jurassic Park film franchise, but is something that has still existed into today's modern pop culture, where often people think Dilophosaurus, they think frill and spitting venom. Unfortunate, but true. Now we're going to get into the really controversial stuff, which is some of my favorite things. And we're going to start, of course, with, I'm sure you recognize this creature. This is our beautiful Velociraptor. probably one of the heroes or villains of the film, depending on how you think of movie monsters. Who could forget those eerie calls, being chased in the kitchen, you know, these very bright, intelligent-like raptors. But like with the Dilophosaurus, of course, this is actually a completely made-up creature. So this right here is an image of a series of raptors. And if I were to ask you, okay, pick out the Velociraptor on this image. Well, I bet that the dino weenies out there in the crowd would probably know where to point. That's okay. But the majority of people are probably going to look at one of the larger ones and say, that's the Velociraptor. Well, in fact, this little creature right here is actually the Velociraptor. And as you can see, it too has feathers. It's not a scaly lizard. It is in fact a small, about a medium-sized dog animal that lived in Mongolia. So again, it would have never actually interacted with your T-Rex. And it primarily had long, beautiful, dynamic feathers. So the the Jurassic Park Velociraptor also has a pretty strange feature where they actually have broken wrists. The skeletal Velociraptor, its hands actually face inward, kind of like it's almost grabbing a ball. It doesn't have these weird puppy dog begging sort of position. Additionally, the Jurassic Park Velociraptors are extremely, extremely skinny. Feed those poor darlings. These guys would have been absolutely beautiful. They would have had beautiful plumage. They would have definitely lived in groups. And like earlier, we know that they would have had feathers due to the evidence that we find on their bones. Now, I'm sure everyone that sees this might be a little bit disappointed to hear that these wonderful, big, scary movie monsters are in fact little pint-sized birds. But let me just tell you this. If you've ever been chased or attacked by a goose or a swan or a chicken, I definitely would still not want to mess with Velociraptor. I mean, they still have those sickle claws. They could take you out by your knees. I would certainly still not mess with them. I think they're perfectly capable of being a total movie monster. And just for the record, they could have solved a lot of their problems in the Jurassic Park film franchise if only they had reinstalled different doorknobs. Doorknobs forever. Get rid of these handles nonsense. So now that we've kind of laid our poor Velociraptor to rest right now, let's go ahead and talk about the king or the queen of dinosaurs, of course, our beautiful T-Rex, Tyrannosaurus Rex. Now, overall, the Jurassic Park franchise did actually do a really good job with T-Rex as far as updating how it looks. Keep in mind that T-Rex, up until this point in 1992, was still kind of seen as an upright, tail-dragging sort of animal. There are quite a few T-Rex skeletons in museums that were still in the incorrect pose. And so it was really neat to see on the silver screen I actually correct T-Rex skeletal image. And who can say no to this ending theme of it roaring with the banner falling around it? Still pretty incredible. But unfortunately, they did get quite a few things wrong about T-Rex, and these still have repercussions still to this day. Primarily, this is an animal that is literally starving. This is an animal with no muscles whatsoever, except a weirdly beefy thigh. So if you look at the T-Rex that is done in the original film and in the progressive films afterwards, it is a victim of what we like to call shrink wrapping. So shrink wrapping is where you take a skeleton of a dinosaur and you literally just lay skin around it. You don't build up muscle, you don't build up connective tissue, you don't build up fat. And so even though on the screen it doesn't look weird to us, if you know anything about animals, it actually is an animal that is in really, really big trouble. So this might explain why T-Rex was constantly so angry all the time. If I was only getting goats every few days and I looked like this, I would definitely be ready to kill whoever I saw as well. But additionally, it just is not correct. It's the wrong image. I also just want to point out that this whole idea of stand still and it can't see you, I have no clue out of what magical area they pulled that idea. It does not exist. There's no evidence for it, not only in the fossil record, but there's also no evidence in nature. I mean, let me just tell you, go out and do that to a bear and see how that's going to work for you. I can guarantee you they can see you. T-Rex was more than capable of seeing the stuff in front of them. Standing still never worked. So I'm about to show you what the most recent and most scientifically accurate T-Rex is. Is everybody ready? Okay, deep breaths. We'll get through this together. Here it is. So I can hear the screeches all the way here in Dallas. This guy looks chunky. He looks fat. That doesn't look like my T-Rex. And I understand it is definitely very different than what we've gotten used to see. But this, in fact, is a reconstruction of a T-Rex that is correct and is as scientifically accurate as we can possibly make it. Major shout out to the artist R.J. Palmer, who did an incredible amount of work into getting this thing as scientifically accurate as possible. Now you'll notice that I did include another image of a T-Rex that is feathered. This is something that is still in some contention within the science about whether or not T-Rex had feathers or not. And unfortunately, I don't have the time to get into it tonight. But I would encourage you to go out and do the research on feathers and if T-Rex had feathers, because it's a really interesting point of contention right now among the scientific paleontologists. But one of the reasons that this particular reconstruction of T-Rex looks to people like it's fat and it just looks so strange is the original T-Rex that they based the movie off of was actually missing part of its skeleton. So here's a skeletal reconstruction of T-Rex, and at the time that the movie was put together, even scientists had yet to discover this part of the body, which are these lower belly ribs called gastralia. And these gastralia is what really gives this animal its more rotund feature. Of course, up in the upper left hand, this is Sue, the dinosaur, a very famous T-Rex. And you can see the musculature that RJ had put under his skin, showing these attachment points with the ribs. And that's what helps hold up the guts. It's what gives the animal a lot of muscle attachment points for its neck and its legs. So the gastralia is actually incredibly important, and that's what makes it look like this. So keep in mind, this is a starving hell beast. This is a wonderful, happy, loving T-Rex. I do want to point out as well, another area in the movie, of course, is the T-Rex chasing down this Jeep as they are trying to escape from it. And I do particularly love this screenshot because if you notice, it says objects in mirror are closer than they appear. And I think that's so funny with a roaring T-Rex on the glass. But unfortunately, again, destroying hopes and dreams. There actually was quite a few scientific studies around the biomechanics of T-Rex, and it was determined that T-Rex were not capable of running. They could certainly get up to speeds of 10 to 15 miles an hour, so if you were on foot, you definitely could not outrun this guy, so I would not recommend trying to run from it on foot. But if you were in a Jeep going 35 miles an hour, you were totally fine. Don't worry, Jeff Goldblum was never in any danger. It's okay. So the Jurassic Park T-Rex continues forth to this day, and you see it in incredible amounts of media, from toys to whatever the hell Pixar was thinking that they were doing with The Good Dinosaur. Of course, you see a lot of memes, but you are always presented with this shrink-wrapped dinosaur, this skinny, roaring animal. You're still missing the gastralia. I will say on the majority of these reconstructions, it still is missing the gastralia. But I also want to point out, because you see a lot of these memes about its arms, I just want to take the moment to defend T-Rex's arms to everybody out there listening. Yes, they're small. Yes, they look ridiculous. But it's actually been proven that T-Rex had an incredible arm strength of being able to lift about 300 pounds just by one arm alone. So anybody that wants to go after a T-Rex, I can guarantee you, you're still going to get flipped through the air by this particular dinosaur. And I will just say, as far as what they use the arm for, We are not entirely sure, unfortunately, because again, since behavior doesn't fossilize, it's always speculative, it's always a hypothesis. And the two leading hypotheses right now are that they, one, use their arms to push off the ground to help get them back into a standing position, because T-Rexes would rest when they're sleeping, they'd rest crouching, almost like a chicken does, on the boot of its pelvis, and so they needed their arms to help push their gigantic heads back and get the momentum to stand up. Or they used it to actually clasp either their food while they were tearing chunks out of it, or they actually used their arms to clasp a female T-Rex while they were mating and making baby T-Rexes. So we're not entirely sure, but we do know that these T-Rexes were using their arms. They were very, very strong, so we need to stop making fun of them because they could absolutely destroy us with their arms if they wanted to. After the 1992 Jurassic Park film, of course, there were more films, and I'm not going to take the time to get super into them, although I will say the heinous crime committed by the third film was the fact that this woman did not die. Whoever thinks bringing a megaphone to a jungle full of meat-eating dinosaurs and screaming into it nonstop, I don't know. She should have died. I will go on the record saying she should have died. The one character that they did introduce to us in these films, of course, is the Spinosaurus. And I will say at the time that these films were first made, this is in fact what we thought Spinosaurus looked like. Unfortunately, the only Spinosaurus specimen ever discovered was actually back before World War II. It was actually destroyed in the museum in Berlin when they were bombed by Nazi Germany. So for the longest time, we only had drawings of these skeletons, and so we did believe that this is what it looked like. Well, I will just say, and again, I can hear my paleo fanboys in the group right now shouting at me. Back in 2014, and now a new paper in 2020 has finally given us more skeletons of Spinosaurus. It has updated its look, and this is actually a much more accurate reconstruction of Spinosaurus. It still has the tail, it was still gigantic, it was still dynamic, but it probably lived a crocodile-like lifestyle where it actually lived in the water most of the time. And I want to go on record as just saying it doesn't matter who would win in a battle, Spinosaurus or T-Rex, because they would have never interacted at any point in their lives. Yes, they did overlap a little bit in geological time, but Spinosaurus would have been a fish-eating dinosaur, maybe even occasionally a carcass in the water. T-Rex lived further away from the edges of large marshy shorelines and would have never had any intention of fighting another big predator. So I'm sorry, I will not engage in debates on who is about to win. So moving forward in the Jurassic Park franchise, 2015 rolls around, and we have now experienced 20 years of incredible scientific information. We're experiencing a dinosaur renaissance where we are just know so much more about what is happening with this whole world of dinosaurs and what they're doing. So as you can imagine, as a paleontologist, when I heard there was going to be a new Jurassic Park film, Jurassic World, I of course got really excited because I was like, okay, here's an opportunity for them to do like they did in 1992, which was take the science and update the audiences on what they're going to see. And because I am a massive nerd, you know I made a costume and I absolutely had a photo shoot in preparation for the premiere of the film. And I still to this day have this shoot. So if you ever see me at a Comic-Con, come up and say hi, I'll be dressed like this. But myself and my fellow paleontology interns at the time, we were very excited. We went to the theater, all of us were in costumes, we're sitting in the audience, we watched the 2 hours. We then leave the theater and we realized that unfortunately the Jurassic World franchise did not do what we were hoping. In fact, it even went backwards beyond the original film. And so this deserves a whole talk to itself. But again, I'm not going to get super deep into this one. I'm just going to point out the highlights or lowlights, if you want to call them, specifically what they did or didn't do with some of their dinosaurs. So again, the Jurassic Park franchise did a really great job of updating the skeletons, of bringing some of that new science to the silver screen. The Jurassic World film regressed those skeletons. In fact, its Stegosauruses are now back to a tail-dragging, slow-moving, dumb lizard. The T-Rex in this film is still starving. For God's sakes, would somebody get this poor dinosaur a proper meal? And I particularly love the Velociraptors, not just because they're still not feathered, they're still too big, but in this particular image right here, Blue's arm is actually broken. There is no way the upper arm bone of one of these dinosaurs could bend that far backwards. So they didn't even bother to try and get skeletal accuracy, let alone the soft tissue accuracy. And I will say on my searching, I did come across this image. If Jurassic Park wanted to, they could have had a really cool, interesting Blue that was a little bit more scientifically accurate. And I would argue this is just as scary and interesting and dynamic as the original scaly reptiles are. So just a side note. But some of the new characters that they introduced in the Jurassic World film is this guy right here. This is the Mosasaurus, of course, a very interesting animal. It's not a dinosaur, it's a swimming reptile. And of course, it was somehow eating a giant shark, orca style, at this film. And those of you here from Texas may be familiar with this animal, the Mosasaurus. So it's not really this horrible, scaly, shark-eating monster that we're used to seeing. In fact, at the Perot Museum of Nature and Science, where I work, we actually have one of these dinosaurs on display from Texas, Dilophosaurus, which was one of the largest mosasaurs that swam in the ocean. But if you look at this comparison of the Jurassic Park mosasaur to a regular mosasaur, you can see the proportions are just completely absurd. And additionally, this mosasaurus, and this is my favorite thing of all time, this mosasaurus in the Jurassic World film franchise is actually larger than a great blue whale, which is the largest animal to have ever existed on this planet. So not only are they just ignoring the fossil evidence, but they're now going to absurd, unrealistic sizes for this animal. I mean, my God, let's just do a basic biology lesson and you can find out why there's no way this thing could exist in the ocean. Yeah, anyway, I'm getting spicy. I'm going to reel myself back. This was another animal. We weren't necessarily introduced to it because you remember in previous films there were pterodactyls in those films, and so there wasn't anything new or interesting to these films, to the how they portray them. But the main issue was primarily the fact that they have a sequence of these animals diving in and lifting fully grown adults up into the air and actually getting quite a bit of air. And so this is an issue because, first of all, pterodactyls are not that big. They wouldn't have even really been able to lift anything the size of a human. But the other thing I want to point out is that, y'all, humans are dense. We are thick. I mean, not from a fat point of view. Our bones are solid, and we have a lot of them in our bodies. We are not meant to be in the air for any length of time. And so just the absolute force and velocity needed by these animals to lift up a solid adult human being is absurd. I mean, physics don't even come close to explaining how this would be possible. And before anyone yells at me that, oh, there were larger pterosaurs, yes, I'm aware there were larger pterosaurs. This one actually is very famous here in Texas. It's called Quetzalcoatlus, and it is the largest pterosaur to ever flown in any time. But again, it would not have been capable of lifting up a heavy adult human. And additionally, they didn't portray Quetzalcoatlus in Jurassic World, so I'm not even willing to give them a benefit of the doubt. The one thing that the Jurassic World film did correctly is this cameo right here by Jimmy Buffett. Yes, that is Jimmy Buffett. I hope that if I'm ever in the situation of where I am being attacked by deadly monsters, my first thought is to grab not one, but 2 margaritas as I'm running away. So this man is a legend. We absolutely stan. Love this cameo. Best part of the film. Now, I will just say that I have not watched Fallen Kingdom, which is the newest Jurassic World film franchise. I refuse to. I've had plenty of people tell me, don't even bother. I'm not that much of a masochist that I'm willing to do that to myself. But I have been shown their version of this dinosaur here called the Carnotaurosaurus. And again, like I've beaten into your skulls, hopefully for the last half an hour, it is terrible. This is an animal that belongs to a group of animals called Abeliosaurs. And they are some of my favorite theropods, actually. They are so interesting. They lived in Madagascar. They lived in India. They lived in Africa. They're really, really interesting. And this is what this dinosaur should actually look like. Look at that wonderful, sweet baby. I mean, he just wants to be your friend, for God's sakes. Look at this dinosaur. But additionally, I want you to notice specifically it's, again, a healthy weight, so it's not shrink wrapped. And its arms are actually rotated backwards. Abeliosaurs are really, really interesting because they, unlike T-Rex, were actually actively evolving their arms away. They were vestigial structures. They were not being used hypothesized not being used by the dinosaurs. So they're completely tiny, flimsy, and ridiculous, and absolutely gorgeous. So I just want to reiterate, this is a complete hell beast. This is a beautiful, sweet baby boy. And if we are going to make fun of any dinosaurs for how ridiculous their arms are, I fully present to you Abeliosaurs. I think they absolutely deserve to be memed the heck out of because they're amazing creatures and I love every single one of them. So the Jurassic Park World franchise, unfortunately, did not do very much to update the science. It refused to even acknowledge the science even existed. And it was something that was not only incredibly disappointing to me as a fan of the film franchise, but also incredibly disappointing to the paleontology community as a whole. But you might ask, well, Hillary, why does this matter? It's just a movie. It's just a monster film. They had some flimsy excuse about how they used frog DNA and therefore they can't be feathered. Why does this matter? Well, I mean, it's a fair question. Why should we care so much about a movie or a film franchise? And I would just like to point out that especially the Jurassic World film, it wasn't just some movie. It ends up, if you do a quick Google search, it's on multiple lists as one of the top 10 highest grossing movies of all time. And what that means is that millions and millions of people saw these films, and for some of them were first introduced to dinosaurs through this film. It meant that millions and millions of people had to stare at a broken-armed blue for at least 2 hours. And unfortunately, that is so embedded in the psyche of everyone in the population that it just doesn't it become apparent to them that perhaps this isn't the correct portrayal. We've gotten so used to seeing this from these films and from other media that is inspired by Jurassic Park that we don't think there's anything wrong. Again, when you Google search Velociraptor, you are more likely to see this sort of a reconstruction versus this sort of a reconstruction. And yes, I understand it's Hollywood, it's a monster film, but the influence of the Jurassic Park films cannot be minimalized. They do make their way into educational content, and I will say I use educational very loosely because the next thing I'll mention just really quickly is this most recent Discovery Channel reality TV show called Dino Hunters, and oh boy, I could do a whole hour-long talk on just the problems with this show alone, but this is something that is on the Discovery Channel. It is presented as educational content. It is something that is presented to audiences across the United States that tune in to Discovery expecting to learn something. And if you look at their reconstruction, you are still presented with a Jurassic Park-inspired, inaccurate, shrink-wrapped T-Rex. This continues to percolate into our pop culture. It continues to be incorrect. So we are always influenced by this particular version of T-Rex. And I'm using T-Rex as kind of the golden child for the entire thing, but this also it stems from the fact of ceratopsians and chylosaurs, other dinosaurs that made it into the Jurassic Park franchise and since have been made into toys and other kids shows and books and stuff like that. Everything is inspired by the Jurassic Park film. It has incredible reach still to this day. Real world science continues to change. It doesn't stand still. It didn't start in 1992 and it didn't end in 1992. Additionally, if I were to sit anybody down who is not a dinosaur fangirl or not a scientist like myself and show them a picture of a dinosaur, they would expect to see a T-Rex or an Allosaurus or an Ankylosaurus. But if I were to show them this, a good portion of the population might not realize that, in fact, birds are dinosaurs. They're not a cousin of dinosaurs. They're not an ancestor of dinosaurs. They are dinosaurs. In fact, dinosaurs did not go extinct with the massive meteorite impact 66 million years ago. No, they survived, and they live around us today. We, in fact, eat a lot of them in our day-to-day life. So the next time that you're snacking down on chicken nuggets, specifically dinosaur-shaped chicken nuggets, you are literally eating a dinosaur nugget. And I think that's pretty wild. But again, it's not something that a lot of people know, which is really unfortunate. And it also has people knowing has real-world impacts. So staying with the chicken for a second, the chicken is something that is really interesting because, again, it has a lot of evolutionary ties to theropod meat-eating dinosaurs that would have been more common in the dinosaur age, in the Mesozoic. And so there's actually been a long-running, almost 20-year project where they take the genetics of a chicken embryo and they go into the genetic code and they're able to identify and work out what turns it into a chicken versus a raptor dinosaur. What causes its tail to be short? What causes it to not have teeth in its beak? Why does it have, wings instead of a hand claw? All that sort of thing. But additionally, despite the fact that this is kind of cool, and who knows, maybe in 50 years we may have little chicken raptors running around in our backyard, it also has real-world connotations where the information that these scientists are getting from going and picking through a chicken embryo DNA, they're able to figure out mutations that cause cancer. They're able to help identify mutations in the genetic code that potentially could cause long-lasting, horrible disabilities in both young kids and potentially older adults. We're able to take the science that they're doing of just trying to de-evolve a chicken and actually apply it to real-world science today. And if people don't know about this, unfortunately, it means that they don't get funded. So if we're perpetuating the wrong information, it does have real-world connotations to the real science actually being done in the background. Another project I do want to point out for just a moment, because I find this incredibly interesting and fascinating, is the De-Extinction Project. This is an active science project that's being done right now, where scientists are actually going into museum collections and looking at animals that recently went extinct, for example, like the passenger pigeon or the great auk or the Thylacine, where museums still have their skins, they still have their skeletons, so they still have their genetic DNA. And they're actually actively working on trying to figure out how to bring some of these animals back from extinction, reintroduce them into their environments, especially those animals that went extinct due to human interaction. Now, of course, with this project, there is a ton of both moral and ethical questions. I'm not necessarily saying I'm for it or against it, but it does have some incredible ideas and potential repercussions for our environment and for animals and what humans' responsibilities are to the environments that we impact. So the De-Extinction Project is very interesting. There's wonderful TED Talks about it. I highly encourage you to continue learning about this. Like I said earlier, we are in the middle of a dinosaur renaissance. And the majority of people, if you're not a fan of dinosaurs, if you're not scrolling the dinosaur social media like I am all the time, you may not be aware of this. We have named more new species in the past 20 years of dinosaurs than any other species of insect or birds or fish, anything living today. In addition to just naming new species, we also have an unprecedented understanding of what the world looked like back in the Mesozoic, back in the Cenozoic, even in the Precambrian before dinosaurs. And by understanding what these earlier planets were like, the climate and the plants and the animals and the ecosystems, it also can be directly applied into what we're experiencing today. We are experiencing a shift from an ice age world into a hothouse world, and it is happening at a very rapid pace. Climate change is happening. So therefore, we as humanity don't know what to expect from a hothouse world. Well, guess what? Dinosaurs lived in a hothouse world. So by looking at the plants, what Bonnie Jacobs does at SMU, by looking at the dinosaurs, we can understand maybe what to expect of our own world. But just to kind of highlight this whole dinosaur renaissance, just how absolutely insane the science is in this day and age. In one day, back in early 2020, of course, before the pandemic hit, there were 3 new species of animals named within hours of each other. The first, of course, was the Spinosaurus aegyptocus, and it wasn't a new dinosaur necessarily. They were just publishing the new information about its tail, that it was a paddle-like tail. So not only was that absolutely credible, it blew up paleo Twitter like you wouldn't even believe. But just a few hours before that, they had named a new species of ceratopsian, Stegosaurus and Selle, from Montana and Lower Alberta. So again, just a few hours before that, a brand new ceratopsian dinosaur is. Look how incredible that is. And pulling up the rear, not to make anyone else feel like they're being left out, they named a brand new species of giant mammal from the Cretaceous. And keep in mind, mammals during the Cretaceous were the size of rats. So the fact that this animal is the size of a small dog was pretty incredible. And additionally, this animal was found in Madagascar. So in one day, you had 3 new species with incredible impacts in the scientific world. And this is something that you may not see. These are certainly not stuff that's being promoted on the silver screen or even in kids shows or books. So I also want to point out that not only has the science been changing, but paleontologists are changing. And let's be honest here, when I say paleontologist, how many of you picture Alan Grant first? And I will just go on the record saying that Ross is not a paleontologist from Friends. I refuse to accept him as a paleontologist because that man never held a rock hammer the entire time in the show. So he does not count. But even myself, who I am a paleontologist, I'm a professional paleontologist, when I picture paleontologist, I do think of Alan Grant, that stereotypical white man with the bandana, the hat, the sunglasses, all of that. And to be fair, in the early 90s, that was a lot of what people were seeing in paleontology. They were seeing, again, this stereotypical Alan Grant sort of paleontologist, from Jack Horner to Pete Larson to Bob Bacher. And unfortunately, the 2015 Jurassic World film did very little to actually update that stereotype. It actually fed into it more, and in some ways made it worse in a lot of ways. But that being said, we did get sexy Chris Pratt, and despite as problematic as his character is, I will be forever grateful to this film franchise for letting me stare and drool at him for a couple hours. Additionally to how paleontology is portrayed, when you picture going out on a dig, this is what you probably picture. A beautifully articulated skeleton laid out in the ground that you literally just take brushes and you brush sand particles off of, and suddenly you have a fully formed dinosaur at your feet. Or if you maybe don't know where to look, you can use this special technology to take images hundreds of meters into the ground, and you can discover skeletons that way. I admit, before I went on my first dig, this is also what I imagined. This is also what I pictured, because this is the only thing that had ever been presented to me through the silver screen and through Jurassic Park. But again, even to this day, this just isn't correct. And in fact, fieldwork involves a lot of this. A lot of tears and screaming and breaking because you just shattered a crocodile vertebra right before your boss came around the corner and witnessed it. It's going out in the field and it's trying to get your stupid curator to get his dumb face out of your field photo so you can show your dad this cool Triceratops skull that you found on your birthday. It's crazy shenanigans involving dinosaur onesies being worn at professional conferences. It's going out into the field and sitting around a campfire and just hanging out with some of the most incredible people in this world. Not only professional paleontologists, but people of all backgrounds and all walks of life. It's sitting around in a cook tent watching the Jurassic World film out in the middle of Utah when it's a rain day and you can't go out looking for dinosaur bones. It is most of the time only finding fragments, but still being able to gain an incredible amount of information from the fragments that we find. And so it is something that is way more rich and interesting and diverse than what you may see. And no, unfortunately, we never find fully articulated, beautiful skeletons. Heck, we start chugging vodka when we find 3% of a skeleton. That's a big, big deal to us. So it just unfortunately doesn't really say what's true. And if you don't know what's true, it also means that you're potentially being cut off from funding opportunities. There are people out there that may not realize that this is accessible for them, that they could go and do a dig themselves, that it is actually an incredibly warm and inviting community. You don't have to have a master's or a PhD in order to go out in the field. And I would just like to point out that the women of paleontology very rarely get to be on the silver screen, but there is an incredible amount of women in this field that do so much wonderful science. And specifically, I would like to just recommend these particular social media accounts on Twitter. If you're looking for paleontologists to follow that are diverse and interesting, come from a wide range of backgrounds, and offer lots of different viewpoints on dinosaurs, on invertebrates, on whales. It's such a wonderful, broad community. So the last thing I'll just preach at you before I get off my platform here is you should care. You should care that what you are engaging with, whether it's a $11 movie or a book that you picked up from the library, is presenting you with the facts. Especially in this day and age where it's really, really hard to tell what is real, what is fake news, what is science, what isn't. You should definitely try to do this in everything that you do, where you seek out sources, you seek out more information, even when it comes to T-Rex. So I just want to end and say thank you so much for staying with me for this whole time. I am so excited to get your questions and chat with you more. You can feel free to follow me on social media. Feel free to follow the Pro Museum. And I will just say really quickly about the Pro Museum, because I'm sure some people are interested. We are reopening to the public. You will need to purchase your tickets in advance, and we will be open tomorrow and Sunday, and then Friday, Saturday, Sunday moving forward. So I'm really excited to hopefully see some of y'all back in the Pro Museum and peering at me in the Fossil Prep Lab. So thank you so much.
That was absolutely fantastic. So I'm warning you both. We have a ton of questions, so
wonderful.
Probably we'll just go on until we've answered the questions, or if it's just too late and we can't handle anymore. But yes, that was amazing. I actually want to start on something that has been brought up. That's a pretty good question. So what exactly is a dinosaur? So so we're talking about where you have, like, you said this was like a swimming reptile. It's not a dinosaur. And then I realized that Dr. Jacobs, I don't think your stuff counts as a dinosaur. So what is a dinosaur?
No, absolutely. That's a really good point. And it is something that unfortunately I don't always think of because I'm just so used to knowing this information. So a dinosaur is a branch of Archosaurias, a branch of reptiles, although we now refer to reptiles as a really big taxon. It's not actually a proper name anymore, but because if you want to say reptiles, in fact, mammals could be considered reptiles as well, but we won't get into phylogeny. So it is a type of animal that is an upright position versus the more sprawled position like crocodiles. It has a very unique bones in its skull. It has very unique bones in its hips that make them different than crocodiles. And the reason why I refer to things like Quetzalcoatlus or Mosasaurus as swimming reptiles, they do not have these unique characteristics that just dinosaurs have. Dinosaurs are actually really interesting in the fact that they're actually how they breathe is completely unique from any other reptile. So there are skeletal indications within the skull and the hips, like I said, but also their upright posture. We also know about their metabolism, how they interacted, how they breathe, that also then puts them firmly in the dinosaur category, not the reptile category, like crocodiles and mosasaurs and Quetzalcoatluses. That's a very quick and dirty introduction. I won't go into too much more because then we're going to be here for days trying to figure out phylogeny, and without images it's a little hard to show everybody.
That makes sense. So actually I want to explain a little bit more. So one of the things is we're talking about paleontology, right? So everyone's thinking, like you said, like we're assuming we're going on these digs, we're seeing these giant dinosaurs, but like Dr. Jacobs, you do botany, paleobotany, right?
Right.
So what is the difference between what both of y'all would look at? Like I assume, and I guess also who would be looking up the ancient crocodiles then? So if Hillary, if you're more into the dinosaurs, and who's caring about the reptiles? And then Dr. Jacobs, how do you Dr. Jacobs, let's start with you before I go on to too much, but like what defines yours? So you're paleontology, but you're not dinosaurs. So how would you define?
So fossils, but anything to do with plants. And so there are places where you can find fossil bones and fossil plants in the same horizons. Not commonly, but it happens. And so, for example, here in Texas, down around Glen Rose, and in fact, there are some specimens that are on display at the Perot Museum that I worked on with a colleague that are found right in with a whole bunch of sauropod dinosaurs. And so these are conifers, they're plants that produce cones, and the female cones, which are larger, and the male cones, which are smaller, were found in with the little stems and the minute little leaflets that are on them. They're kind of like junipers, which would be mountain cedar in Texas terms. So you can see that at the Perot Museum, and those fossil plants were found right in with dinosaurs. But most of what I work on actually is not as old as that. That's like probably like 112 million years old. So usually what I work on is something between about 65 million and, I don't know, even a few hundred years old. So, but most of my work has been in Africa, and it's been the younger age. So after the dinosaurs were gone in the form that we're used to thinking of them, but they were still around, of course, as birds. Hillary, that was great. Actually, the whole talk was really fun.
That's wonderful. I'm so excited you enjoyed it. I just want to point out, I don't want Bonnie to sell herself short, because I feel like paleobotanists get the short end of the stick most of the time. Their work may not be quite as sexy as dinosaur paleontology, but by understanding the plants and leaves, that is the key to understanding everything about how dinosaurs lived.
Yes, exactly.
Yes. I think paleobotanists should get way more superstar attention than they do. Unfortunately, sorry, Bonnie, leaves are boring.
No, they're not. No, they're the best. These are the best.
But again, you can understand climate through the leaves. You can understand everything through the leaves and the roots. No, roots. Dory's going to kill me if I say roots. Roots are useless. But stems and everything like that. And so to answer your question too, as far as in regards to who does what, anything with a backbone usually falls under the umbrella of vertebrate paleontology. So that might be mammals, that might be fish, that might be crocodiles, that might be dinosaurs. And as a scientist, when you're going through school, you are encouraged to focus on a specific subject, a specific group of animals, or a specific group of time, or even a specific formation. So for me, I spent the majority of my career focused on late Cretaceous terrestrial dinosaurs, because at the Denver Museum, that's what they studied as well. So I know a ton about Utah and New Mexico and the Hell Creek Formation, but I know very little about the oceans of Kansas, or what was going on in California, or what was going on in Africa, because I just was never exposed to those fossils. So when you go out in the field, what you want to try and do is you want to try and invite as wide a range of scientists as you possibly can. You want to invite the paleobotanist. You want to invite the crocodile expert. You want to invite the fish person. So that way, all together, you are finding stuff and you are discovering things, and you're able to mesh your two sciences together to get a complete picture. I also will just say, part of my paleobotany comes from the fact that many times in the field, I will be hiking out every day, 8 hours a day in the hot sun, climbing those hills, and I'll see something shiny, and I'm like, this is it. This is the moment I find a dinosaur bone. And I get up to the top of that hill, and it's a piece of petrified wood. And you could just see my soul leave my body in that moment as I realize I've found a stupid piece of wood. Actually, as much as we love our paleobotany and they have incredible science, us vert paleo people tend to shake our fists because many of us have been tricked by petrified wood before.
So that actually is great, because there's this other question of like, how do y'all know where to start digging? How do you know that this is the spot that I'm going to find either some petrified wood or bone or something? How do y'all do that?
Sure. Sorry. Yeah, I can start, Bonnie, if you want to add. So we first start by identifying, again, what we're interested in. So again, like Bonnie said, she's interested in a certain range of time. So she's not necessarily going to go out looking at rocks that are older than her study is interested in, right? If I'm looking for late Cretaceous dinosaurs, I'm not going to bother trying to go find Jurassic age rocks, because that just doesn't give me the study site. Once we've identified kind of what we're interested in, we then need to look at a map. We need to look at a map of the area that we have access to, whether it's the United States or Africa or Asia or whatever, and find areas where rocks are exposed. They're not covered up by plants or trees or vegetation. So you can actually see the rock, you can see the bedrock. And then when we go out there, we then can use topographic maps, which are put together by geologists that help to identify how old those exposed rocks are. And we focus our attention, we say, okay, this group of rocks are old enough. They're terrestrial, so they probably are going to have terrestrial animals like dinosaurs in them. You go out there, you set up a camp, and then you hike every day looking at the ground, hopefully finding something. Most of the time, not finding something. So I don't know, but I will say vert paleo is a little bit different than paleobotany. So Bonnie, I'm sure, I know, in fact, paleobotanists do it a little bit differently than we do.
Yeah. So it's, the first part is the same, because you have a research question, you have a significant research question that you're going after. And so because of that research question, you want to look for rocks of a certain age and so on. And so you use all the publications, all the work that's been done before, if there has been any work done before, and usually there's something. And you use those as clues as to where you might find what you're looking for. But what's really interesting and wonderful is that different, your own experience gives you certain search images. So I could be in the field with a vertebrate paleontologist, and we're walking together, and I'm looking for plant fossils, and this other person is looking for bones. And, this other person, this actually happened to me once, all of a sudden goes, oh, wait, and reaches down and picks up a huge, enormous fossil tooth from, practically under a bush. And I never would have seen that. And it's so frustrating for me, because I would love to find some fossil teeth. But, for the most part, my eyes go to things that will pop out as plants. And so it's really great to be in the field with a whole variety of different kinds of scientists, as Hillary was just saying, not only for your collaborative work to get answers to your questions, but also because different people go about the work in different ways. Now, what we do to get an idea of paleoecology, so what you usually ask from the plants is, what was that world in that place like at the time these plants were alive? And so you want to collect a lot of specimens. And so if you work with leaves, like I do most of the time, or even fruits and seeds, you want to have a huge collection. So you hunker down, as my vertebrate paleo colleagues would call it.
Yeah.
You stop and you hunker down and you excavate, big assemblages of leaves or fruits and seeds, what have you, so that you have a really a statistically robust sample of what was deposited whenever it was, millions of years or thousands of years ago, into those sediments. You collect it. If you can, you take it all back to the lab, or you take it all back to a museum. Sometimes, if the flora is easy enough, you could actually do a census in the field. So you tick off, I have this many of this one, I have this many, but you have to be very organized and very specific, and be sure you know exactly how much area you're collecting from and how many leaves, how many specimens, because later, when you do your analyses of the data, you want to be able to know how many specimens, how many different kinds you have. Even if you don't know the species name, you know if this one's different from that one, how many of each taxon you have, what their shape is, what their size is, what the depositional setting is. You want to work with the geologist to understand the mineralogy of the deposit, to tell you more about the environment that those plants lived in. So to piece it all together, you really have to collect a lot. So we talk about hundreds of specimens from a small area, whereas somebody studying large fossilized animals obviously would be talking about, on a different scale.
A limb bone. We get excited about a piece of a skeleton.
Yeah.
So that actually, there is a different question. I'm going to reword it a little bit. So you talked about, Hillary, that you would get, like, if you got like 30% of the skeleton, you were super excited, right?
3%, not even 30. 3.
Okay. I was thinking that was like, no, there's no way. That's too small. It was, you didn't say 3.
No,
okay.
It is.
But Bonnie, so whenever is it just that there is so much more flora out there that you're able to find so much that you're like able to say that I have so much of this one type? Well, I guess I'm saying so much figuratively. I know you're still limited, but like, are you able to find like, is it portions of the flora, or are you able to find like large amounts of it? Like, do you know there's a forest there type thing?
Exactly. Yes. That's the answer is yes. And, but of course, not every site is as productive as every other one, so sometimes you really have to work at it hard to get enough specimens that, you feel satisfied that there's different levels. So there's the original plant community. Let's say it's sparsely vegetated. Okay. Let's say it's not a forest. Let's say it's, like kind of an open wooded or shrubby area. So you don't start with as much. And then maybe the environment of deposition is such that not everything gets preserved, or maybe it doesn't all get concentrated very well in the sediments, right? And then you come along and then you sample that sample. So, you might have to work a long time and really hard to get the number that you think is sufficient, or to the point where, you just can't put any more hours in. On the other hand, in recent years, I've been working with colleagues on a place where there's just such a high density of fabulous plant fossils. And so it's kind of like you're in heaven, it's just great. So you can do a lot more with it, so you can sample horizontally, so that represents the same moment in time. You can sample vertically, which, will represent different time intervals, collect hundreds of specimens from each place, and you do a lot more with it, yeah.
And I think also this is a good point is well, first of all, vertebrate paleontology, we do occasionally come across what we call bone beds, and that is
right.
where a significant amount of skeletons manage to all get clustered together and then deposited at the same time and fossilized. But this is also something that I feel like most people don't fully appreciate. It is incredibly difficult for anything to fossilize. The hurdles it needs to get through to actually not only survive burial between scavenging and being stepped on and potentially being churned up by not only other animals and other plants, but even the earth itself, which is constantly moving under our feet, is churning up these fossils, but then survive to the point of millions of years later, it gets to us and we can find it. I can't begin to tell you how many times I've been out in the field and I will see bone fragments on the ground that if I'd only shown up 10 years ago maybe was a beautiful fossil eroding out of the side of the hill. It's just the nature of it. And additionally, you know, Bonnie's referencing depositional environments. And that's the other thing to keep in mind, is that not every environment is going to be conducive to fossilization. So you have environments, say, for example, like a big desert flat area that doesn't have any sort of sedimentary rock depositions happening. The animals there, if they die, their bones are not really going to get buried quick enough or safely enough to fossilize, versus an area like the side of a lake or side of a stream, where these animals are going to get buried pretty quickly by mud or by sand and be protected and fossilized. So even though we understand these areas and we can go out and look for these areas, unfortunately, the majority of the percentage of animals that lived during dinosaur ages, whether it's flora or fauna, will never be able to find, because they were just not in environments where they would have been deposited and then fossilized. So it is unfortunate. It's the sad part of paleontology, for sure, when you realize how much potentially you'll never know. I will just say really quickly before our next question, you know, Bonnie, you tell the story of your vert paleo person finding a tooth and you didn't even see it. Well, funnily enough, I have almost the exact same story, but flipped. On one of my very first digs, before I'd really learned what to look for, you have to kind of train your eye to look for things. I completely walked over a Tyrannosaur tooth. And our paleobotanist at the Denver Museum, Dr. Ian Miller, he saw it and he bent down. He's like, "Hillary, isn't this a tooth?" And I was so embarrassed. I got so much crap from it from the rest of the because our paleobotanist had found a tooth that I completely had walked over. So it happens.
Yeah, he's been looking for teeth forever. You know, he's been out there with those vert paleo people a lot.
Ian is a pseudo vert paleontologist, even if he
there you go.
He isn't.
Yeah.
So how long do you, or like percentage wise, how much of your time is spent in the field versus like in the lab, or I guess y'all call it a lab? I'm not sure for paleo.
Yeah, a lab. Mm-hmm.
Mm-hmm.
I mean, it really honestly depends on where you are and what kind of funding you have and what your ability to actually go out in the field is. Unfortunately, museums and university have a lot of difficulty getting funds. A lot of people, unfortunately, we think paleontology is really cool, but it may not have a great return as far as for universities or even for museums. So it is something that raising the funds to actually go out and do digs is actually enormously challenging and very, very difficult. But if you're lucky enough to work for like a museum like I do, where you do have the funding to go out, generally you try and go out as much as you possibly can in mainly the warm months. Here in Texas, we're lucky because it doesn't get that cold. But for example, if you're working up in Montana, as soon as October hits, there is no way you can be camping outside for any length of time. So you really only have the opportunity to go out and dig from the months of usually May to about September, October. So you are limited in the months that you can do. You're limited by the funding that you have. You may be able to raise funds, but you can only pay staff and camping supplies and food for only a 5-week dig. So you have to get as much done as you can in 5 weeks. And to be fair, although we put a lot of effort into field work, there is actually a massive need for researchers and scientists that don't do field work, that instead go into our huge collections that we already have at universities and museums and actually start doing the research that's needed to understand that. We can go out and collect 7 different skeletons in a season, but if you only have one person working in the collections, those skeletons are going to sit gathering dust for hundreds of years afterwards. So field work is not necessarily it's really fun and it's wonderful and it's incredible to find stuff, but it also is not the make or break it. And I don't want people to think, oh, just because I don't like camping, or oh, just because I'm not physically able to go out and hike, I therefore can't be part of the geosciences. No, we need people that want to do the research. We need the people that are willing to sit in a dusty basement for 3 days just looking at fossils and coming up with incredible scientific ideas.
Yeah, you can put.
Yeah, please.
Well,
yeah.
Right. So yes, same. I mean, the same thing. You know, it costs a lot of money to have the field expedition, especially if it's something far away that you have to fly to, and then that adds a lot of logistical challenges and costs. With plant fossils, it can be a little bit easier in the sense that you can collect sometimes a real lot in a short period of time, and then you take a lot more of your time is spent on analyzing what you've collected and doing the study and doing the publications. Some fossils are microscopic, so if you study pollen, so pollen grains, just like the same pollen grains from today that give you allergies, you collect the sediment itself, and you do the chemical lab work at home in your lab, in your chemistry lab, and you separate the pollen from the matrix, and then it's all a matter of microscope work. So you can get enough samples to study pollen, very quickly, and then you have hours and weeks and months ahead to do the studies and the analyses on those. Yeah. So it just depends what it is you're collecting, how long it might take to prepare it out, to look at your fossils, and then what it takes to analyze them. And the analysis nowadays is so much fun because there's so much fabulous technology now that helps us in figuring out what we have. There's all kinds of computed tomography, that you go into you might get a CAT scan in the hospital, and we can do the same thing with fossils. You can see fossil bones like that, or you can use some other technology.
We send a field jacket that was collected in the 1980s that we have no information for, and if we're lucky, we can send it to a CAT scan and get an image of what's potentially inside. And that's super duper neat because it informs someone like myself, a preparator, or somebody who's actually going to be opening up that field jacket and preparing the fossil out, to know maybe where to open it, what tools to use, to be careful, especially if it's a really old historical jacket.
Mm-hmm. Yeah. And then for microscopic things, you've got scanning electron microscopy. So really high resolution scanning electron microscopy can show you, the submicron scale spines on single pollen grains and all the incredible detail that's so beautiful on individual microscopic fossils. Yeah.
So so we do have questions for your talk, Hillary, but this is going wonderfully. We have so much interest right now. I'd like to keep this talk going.
I will just say again, if you need, I have my social media. I'm more than happy. People wanted to message me their question about the talk. I'm more than happy to answer those. But yes, this is a great conversation. So let's just keep it rolling for sure.
That sounds perfect. As long as y'all just let me know if we're going too long for you two. Otherwise, this is wonderful. We have so many people interested. And one of the things that I'm noticing, we have a lot of people, how do they get involved? How can they help the field? How can they help? Are there rules on collecting fossils themselves that they have the time or the area or anything like that?
Yes. Bonnie, I'm going to take this bad boy.
Yeah, please do. This is your wheelhouse right here.
So yes, what is really amazing about Texas, and especially North Texas, is we have an incredibly enthusiastic group of people here that love to go out and collect fossils. Now, with that, there is a massive caveat that I want to make very, very clear. You cannot collect fossils, especially vertebrate fossils, on federal land. Now, I know here in Texas that's not much of an issue, but if you're on a family trip to Utah or Colorado and you are in a national park and you happen to look down and see a dinosaur bone, you are federally not allowed to collect that. In fact, I have unfortunately been on teams in the past where a volunteer has tried to take something home. It's called a party fossil, and has been met with the feds the next town that they were in, because it is a serious crime and you will go to jail if you do that. The rules are a little bit more squidgy around plant fossils and invertebrate fossils. Unfortunately, sorry, Bonnie, the federal government doesn't view plant fossils quite as important as vertebrate fossils. But I just want to make sure it's very clear that if you do go to an area that is federal land that has dinosaur-aged rocks, by all means, they encourage you, go out there and look, but don't pick anything up. Don't bring it even back to the visitor center. Take a picture of it. If you have a GPS, mark the GPS coordinates and bring that information back. Because like Bonnie was saying earlier, it is not just the fossil that's important. It's the context of the fossil. It is scientifically valuable to know where that fossil comes from, what rocks was it in, what is it near, how big, all that stuff, that data that comes along with it is actually more important than the fossil itself. So as you, as a well-meaning visitor to a national park, pick up a dinosaur bone and bring it back to the visitor center, you have destroyed all scientific potential for that fossil, and you might as well throw it down a cliff and destroy it at that point, because unfortunately it just doesn't have that value to any sort of scientific research institution. Now, that being said, and I will promote them, so if you're here in Dallas, highly recommend the Dallas Paleontological Society has built up a great group of paleo enthusiasts, amateur paleontologists, and I love them. I go with them sometimes too, where they built up relationships with private landowners that do allow people to come onto their land and collect fossils. And if you are on somebody's private land and you have their permission, always make sure you get permission. Do not trespass, okay? You absolutely can take those fossils. They belong to the landowner. If the landowner says it's okay, those can be yours. So I just really encourage you to, before you go out looking for bones, looking for fossils, to do your research beforehand. That being said, I don't want to necessarily say, no, don't do it, because again, sometimes the best ways to find things are to go out and look for themselves. So if you're not happen to be in the Dallas area, go onto Facebook. There are wonderful groups of paleo enthusiasts that they know all the hidden nooks and crannies for shark's teeth and, ammonites and maybe even mosasaur bones and stuff like that. Go onto Facebook, do your research, find a group of people to go with. If you're going to go by yourself, please, please, please be super safe, be aware of hunting seasons and all that stuff. So that's on your own. Now, the other side of it, too, is how do I get involved, like going on a museum dig or a real dig? I sometimes hear that. And I would just encourage you to seek out, if you have a local museum that has a volunteering program. That is the answer. That's how you get to go on these things, is you reach out to a museum and you say, I will work for you for free. And most of the time, these cash-strapped institution will absolutely take you. If you are a sane, good person that can lift a heavy backpack, you'll be most likely accepted to go out in the dig. That's how I got to go. So I am very fortunate in the fact that the Pro Museum, we have a wonderful volunteering program. I have a group of fantastic volunteers. Shout out to all of them watching right now. That I know them, I trust them, and I've taught them everything. So when we get a phone call, hey, we need to go collect a turtle, or hey, a mosasaur is coming out of some guy's backyard, I'm going to call my volunteers first versus reaching out to the community for volunteers, because I know them and they're trained. I started as a volunteer at the Denver Museum, where I volunteered for them for 6 years. And that's how I learned how to prep fossils. That's how I learned about dinosaurs. That's how I met other people in the community. That's how I got my first job. So I am a massive proponent of volunteering. If you don't have a local museum right near to you, reach out to institutions that are doing field programs and just say, hey, if I can get myself to Utah, will you take me? And most of the time they're going to say yes. So volunteer, volunteer, volunteer. That's my big thing.
So we actually have a follow-up question that is very interesting, especially in Texas. I don't know about the other states, of mineral rights. Are fossils considered under mineral rights? So if the owner doesn't own those, is that something that has to be considered?
I don't actually know if I know the answer to this. So I don't want to necessarily give the wrong answer. What I will say is, interesting enough, this very same question came up in Montana recently, because Montana is very similar to Texas, where the majority of Montana is privately owned land. So there was actually a lawsuit brought to the Supreme Court of Montana claiming that fossils were part of mineral rights and therefore did not belong to landowners, and it had, oh my God, incredible repercussions for people, research institutions and landowners, everything like that. And they actually voted no, that fossils are not part of mineral rights. And in fact, if you find a fossil on your land, it belongs to you. So I know at least in Montana, that's what they did. I can't speak to Texas. Yeah, I'm sorry. I don't know the answer to this one. I'm so sorry.
No worries. Any chance you know, Bonnie? It's fine if you don't as well.
Well, I'm pretty sure it's the same as just as you said for Montana. I don't know how to mute myself on this program because I would holler for my husband, who's a vertebrate paleontologist and who was very involved in this exact issue.
You Jacobs is great.
Yeah, so if he's listening, maybe he could come out here and give us the answer. But anyway, yeah, I'm just going to leave it there. I think it's probably the same in Texas as it is in Montana. That's my impression.
Okay,
Yeah.
cool. So we have a few more that are talking kind of about the field stuff before we go into the others. So one of the things is people are wondering about like time and how are things preserved. And so one of the questions is like, how well does seawater preserve the fossils? So like we're always talking about how like you find these fossils that are like on land and everything, but what about on the seafloor? And this has to do with, because obviously the ocean has changed. So this has to do with both the flora and the fauna. And
Right,
so kind of like, how does the sea have to do with y'all's fossil collection?
So it's not the water that preserves the fossil. It's the sediments that go around the fossil that turn that object into a fossil. So it doesn't really matter if it's in the bottom of the ocean, if it's in an area that they get buried quickly and enough that then they are protected from any sort of currents or movement. There's nothing in water that exists long enough. There's no atoms or molecules in water that exist long enough that add to the fossilization process. Again, we're talking millions of years. So it is something that if they're in an environment where you're going to be getting deposition, either a mudslide or a sandstorm or something like that buries the fossil, that then these rocks harden and lithify and become sedimentary rocks. Again, if you know anything about geology, you know the rock cycle. That's where these fossils are being put in. So that's my answer. Seawater has no part of fossilization.
So Bonnie, do you feel that the ocean is maybe taking away or adding to the your part of the research of the plant life or anything like that?
Well, for organic matter, so that's what we want to see from the plant world. We want to see that organic matter preserved, right? Since they don't have bones, they don't have anything, they don't really have much in the way of hard parts. So there are chemical conditions that will be best for preserving organic matter, and that's usually a reducing environment where you don't have oxidation, you don't have oxygen available that could actually percolate with water to decompose, to allow the decomposers to live in there and the decomposition process go forward. So a lot of times at the bottom of the ocean, it is anoxic. There's very little or no oxygen. So that's really good for preserving organic matter. So people might study some organic molecules that are in deep ocean water deposits. But then, out in the middle of the ocean, you don't necessarily get the kind of things that I would study, right? You don't get plant fossils right out in the middle. So you get them. Sorry, what's that?
Sorry, so who would study coral, like ancient coral? Which paleontologist would that go under?
That would be invertebrate.
Yeah, invertebrate, yeah.
Okay.
The spineless one.
Nice one of you.
The spineless.
Someone out there. Okay.
Yeah, oh, definitely. It's a huge field. I mean, it would be corals and all kinds of animals that make seashells. Yeah, that's invertebrate paleontology. Exactly. And speaking about that, actually, if you have very acidic waters, you wouldn't get the preservation of seashells, right? Because they would dissolve in acidic water. The seashells are made out of the same stuff as limestone, the same stuff. Anyway, so with plants, with the organic matter, lake bottoms, ocean bottoms, or a lot of times lagoonal situations. So that in that case, you're in a lagoon, well, it could be low in oxygen at the bottom. You get the organic matter coming in. You're near to places where you have plant material growing. And so therefore, that's a kind of good place to preserve, to bury, and then also preserve plant fossils. Lake bottoms are a great place. Sometimes you get what are called overbank deposits. So you have floodwater conditions. And if the flood covers up the organic matter quickly enough and seals it off from oxygen, it'll get well preserved. So Wait, did I lose track of what you were asking me?
No, that was. I do want to say as well, just jumping up what Bonnie says, speaking specifically about organic material. Again, most of the time when we think fossils, we only get the hard parts. We only get the bones, and yes, those don't usually get affected all that much by oxygen or not. But if the very rare extreme cases that we've gotten soft tissue preservation, so for example, feather impressions on theropod dinosaurs, or these wonderful, they're called dinosaur mummies that actually have a little bit of that soft tissue body that was preserved. Those are usually always found in situations like the lagoons where it's very oxygen poor, and so therefore the organic material is not being decomposed and degraded quickly enough that, again, it gets buried, it gets preserved, and then it manages to harden and fossilize and make it to modern times. So yeah, it can affect the soft tissue of vertebrate animals as well.
Right. And that goes back, you can get organic matter that's millions and millions and millions of years old, right? So you have to get spores and pollen grains, for example. I mean, they're not replaced. They're not turned into stone. They're actually organic matter. It's the heart. It's the shell of not the shell, but the wall of the pollen grain or the spore that you're actually looking at.
I will just say, though, before we get this question, however, you are not going to get dinosaur DNA.
Oh, right. That was the next one.
Most of the time, especially what Bonnie's talking about, millions and millions of years old absolutely is still very, very old, and it's incredible that organic material makes it even that long. But a lot of Mesozoic material, even soft tissue preservation, doesn't have any real organic molecules in it, especially something like DNA. The proteins in a DNA skeleton, well, the proteins in DNA are not found in a skeleton. They're essentially fossilized in rock. So no dinosaur DNA, not even in a mosquito amber. Sorry, it's not going to work.
Well, they were all disappointed, and that was all we were waiting for.
Sorry. I think we lost Bonnie though, or else she
is frozen.
With my answer.
Well, this might be a good time to switch over to questions on your talk while we wait. She probably had some internet issues.
Absolutely, no worries.
Yeah, so let's just go ahead and switch over to the questions on your talk, because
technology.
I feel bad anyway. So I'm going to go ahead and warn you, there were questions through your whole talk, so we're going to be just going through them. So tons of people loved your Velociraptors. So let me organize myself. I wasn't planning on going here quite yet. 1 second.
Okay.
So you talked about Velociraptors. You talked they're small. They have their feathers. Did they fly or did they glide or did they do neither?
Sure. So Velociraptors, and keep in mind, this is behavior. So this is something that it is kind of hard to 100% pin down to 100% understand. So all of this is still being actively worked on. So Velociraptors were not capable of flight. We do know this because their fossils they do have feather attachments, but they were too old to have evolved flight feathers. Now we do have raptor dinosaurs that did evolve flight feathers, and we find them in rocks that are later than Velociraptor, and we find them in areas where we actually have those flight feathers saved in the rock. But Velociraptor is also skeleton. We have fully articulated skeletons. Their arms are not quite evolved enough into a wing that would indicate flight. Their tails were not quite evolved enough to be a rudder to help with active glided flight. That being said, Velociraptors potentially could, use their feathers to turn really quickly. They may have used it for aerodynamical reasons. But what's kind of interesting, and I didn't get a chance to really go into it during my talk, but I will now, is that there is evidence in the fossil record that even the most primitive dinosaurs, so some of the very first animals that we can identify as dinosaurs in the mid-Triassic, have potential evidence for skin integument, so stuff that's on the skin, like my hair is skin integument. So they aren't necessarily going to be your typical bird feather, but they would have been more spiny, more like fuzz. And so people hypothesize that these early dinosaurs were actually using these proto feathers for was potentially body warmth, helping them to regulate their temperatures and keep themselves warm, because if they're tiny, you lose energy really quickly. But also they could have been used for a display purpose. So knowing that even the base of dinosaurs had some sort of skin, skin integument, it implies that potentially the majority of Dinosauria actually had some sort of skin integument. And some of these more derived characters, these derived dinosaurs towards the end of these evolutionary branches like Triceratops and Stegosaurus, they secondarily lost those skin integuments as they got bigger and they didn't need them anymore. So Velociraptor is not quite on the end of the branch. And again, we found evidence of feathers, but these guys were potentially, again, using them for heat retention, even cooling. Chickens actually can fluff themselves out on a hot day and actually completely cool themselves off that way, which is kind of incredible. And potentially they were using their feathers for display purposes. It's much easier to evolve a structure on your skin to be displayed and then secondarily evolve it for some biomechanical reasons like flight than it is to evolve something and go straight into biomechanics. So short answer, no, Velociraptor couldn't fly. Long answer, it had feathers and was using it for a whole bunch of other stuff.
So some people have heard apparently that like they would use their wings so they could stay balanced, kind of like how a chicken, if they're grabbing onto something or like being off balance, will flap. Would the Velociraptor probably held on to prey, flapped, and like kept their balance?
Absolutely. Yeah, and again, it is not just within Velociraptor, but in other similarly sized raptor dinosaurs, it is absolutely possible that they were using the feathers on their arms or even feathers on their tail to kind of balance and to allow them to turn really sharply, or to probably not control their prey with, because that was all done with their claws, not their feathers. But the act of flight, there are two hypotheses on how flight actually evolved, right? That behavior. And one of the thought processes is that you have this raptor-like dinosaur that's already using their flight, already using their feathers to kind of move around. And what they do is they would start these leaping motions that then they would start gliding with their feathers. And those that could glide had an evolutionary advantage of just being able to leap higher, being able to maneuver in the air to catch insects or small lizards. There was an evolutionary advantage to being able to be more maneuverable, not just on land, but also in the air. So that would encourage the evolution of more and more powered flight. The other hypothesis is called a top-down. So that was a bottom-up hypothesis. This is a top-down hypothesis where the idea was that these raptor dinosaurs were more and more getting into trees and climbing and kind of being more in the denser forests. And they would actually leap down onto their prey and glide and control that glide down onto their prey and potentially be able to snag things out of midair. We see that stuff with gliding squirrels today. In fact, that's how we know that modern day bats evolved flight, by first climbing and then gliding and then eventually powered flight. So flight by itself is still very much interesting. It's very much being worked on. We do not 100% understand how it evolved. But yeah, it's flight, and Velociraptors couldn't fly, but they definitely have feathers.
Gotcha. Thank you. And I believe we just got Bonnie back. So hopefully that's all going to be working soon. We'll keep going through. So Bonnie, just so you know, we've switched over to asking questions about Hillary's talk. So you have a couple of seconds to get all your stuff back together. We have a few more things as well. But yes, I'm so glad you're back. Now I see your camera. Yeah, we were worried because I have a whole section just for you, by the way, on just the old plant.
I'm glad the paleobotanist is getting questions too. That's awesome.
She is. She has a whole section. So I have all the questions. I actually, this is a time to shout out for my team. I have a whole team of people who collect the questions, organize the questions. I have my tech team. I get to be the face of Tap Talks, but I am not the one making Tap Talks works. So I will give another shout out to everyone at the end, but just so we know, we do have all the questions. So Bonnie, if you don't mind waiting a couple minutes, if you have anything to add in while we're asking these questions, please do. But we have a few questions about T-Rexes and long necks and stuff.
Okay. Just so everyone knows, I can't stand T-Rex, so you're going to get salty Hillary here for the next 15 minutes.
So actually, I will say there were some that weren't questions, but there were some comments about their arms. Yeah, maybe they can do 300, but only again if they can reach you.
Oh my God. Leave T-Rex alone, people.
How can you? So I will say, so you can talk about, no, seriously, if he can mess you up if he wants to, but like, could I just stay between his legs? How maneuverable can he be? Can he really pick me up and grab me?
No.
Right. Yeah, so he's still, his best hope is just to stomp on me. But so some people, I think this might have to do kind of follow up on your last question of like behavior. Like, how do we know that the T-Rex laid down kind of like a chicken and uses little stubby arms to push himself up?
Sure. I mean, the short answer is that we don't. This, is, of course, is hypothetical. Anything to do with behavior, don't ever take it as gospel, because behavior is always speculative. It's always hand-waving. Until we invent a time machine, we will never really understand 100% what it is. But the reason that folks are hypothesizing that T-Rex rested on the boot of its pelvis is there is evidence through that the muscle attachment, even some rugosity on the boot of the pelvis. So when I'm talking about the pelvis, I'm talking about the kind of the bone that's sticking down in between the legs, ha ha ha. But it has this very large, almost saddle-like boot. And in T-Rexes, it is actually evolved to be a little bit more substantial than other similarly pelvis-sized dinosaurs. But it also had a fatty pad that would have been attached to the bottom of the boot that then also would have been attached to the gastralia. And so really evolutionarily, there isn't a lot of reasons to put in the energy developing a fatty pad unless if you were going to be putting pressure on it regularly. So for example, one of the dinosaurs that we work at here at the Pearl Museum is a ceratopsian dinosaur named Pacquirenosaurus, where their noses, instead of a horn, actually has a flat pad that would have had a fatty pad as well. And the reason for that is because they probably were smacking their foreheads together in potential mating displays or even rival fights. So this fatty pad on the bottom of a boot of a tyrannosaur, the only real reason it would have needed that is potentially to help support its weight and help it be comfortable when it sat. There also is no evidence within the bones themselves that T-Rex slept standing up. And for a predator that large, it's hard for an animal to get up quickly when it's that big, especially if a T-Rex is trying to get quick to go after some sort of prey item, or even if it's being attacked by another T-Rex. So if you're resting in a crouching position, resting on the boot of your pelvis, you are in a greater position to react to a situation than if you were laying on your side. And there's no evidence that they were capable of standing upright and sleeping. There's no locking mechanisms in any of their joints to keep them upright.
Okay.
But again, it's all speculative, so just take it with a grain of salt.
Actually, I guess there was a lot of T-Rex discussion, not as many questions, so that's
not surprised. The T-Rex fandom is one of the largest fandoms out there.
I'm not even gonna comment on that.
Again, I blame Jurassic Park. Okay, there are cooler dinosaurs out there than T-Rex. Everyone, stop going after the most basic dinosaur.
So when all this started, actually, we had a bunch of people asking what the favorite dinosaurs and all were. And Hillary, what's your favorite dinosaurs?
What's my favorite dinosaur? Of course. So my favorite dinosaur is a ceratopsian dinosaur called Dilophosaurus. And it's a really cool ceratopsian. It's a cousin of a triceratops. It's actually much older than triceratops. And they're found in southern Utah. And they're neat because they have short little brow horns and a little bit of a nose horn. But what they're best known for is at the top of their frill, they have two long horns that come off the top of their frill, almost like a devil's horn. That's why they're called Dilophosaurus. I don't know if you can see this, but I actually have Dilophosaurus tattooed to my arm.
That's awesome.
Along with
I was worried that was like, we don't have to take you to show, but no, you have us covered. So Bonnie, you are muted, by the way. If you go to the upper right, you can unmute yourself. Might have automatically. Perfect. I don't know if you have a dinosaur favorite equivalent, or if you have something you would like to say is your favorite. It's your choice.
Well, I was a dino nerd as a kid, so, I mean, Hillary will hate this, but I grew up going to the museum in New York, and I have to say T-Rex was my favorite.
That actually reminds reminds me, some of the things I was wondering, whenever y'all talk about, like, you only get 3% of the fossils. So the fossils that we're seeing in the museums, are y'all just, like, combining a bunch of different ones?
Sure. I mean, and that's a question I get a lot of, actually. So this is a really good question. How much of those skeletons on display are real? And so this is something that I just want to preface by saying museums are not trying to trick anybody. They're not trying to, present you with a false animal. They're not making stuff up. But the reality of vertebrate paleontology, at least, I can't speak for Bonnie, but vertebrate paleontology is that we never find 100% complete skeletons. Even the most perfectly preserved animal is missing portions of it most of the time. So what we do in most museums, this is true for the Denver Museum, the Utah Museum, the Perot Museum in Dallas, is we try and put as much of the real stuff out on display as we have. And then we make what's called casts. So these casts are exact copies of real fossils, but these fossils may be at a different institution, or they may not be, they may have been destroyed, and so all we have left are the molds, and so that's all we can have. And so these cast bones are made out of resin or plaster or foam, so they're not real necessarily, but they are exact copies of real bones. So they're not being falsified, they're not being sculpted, they are as real as we possibly can get. And the reason for this is, again, either another museum has them, another museum has them on display. There may only be one copy of that bone, and so therefore they can't release it to a whole bunch of places, so they make a copy of it, and that's what gets sent out. But every museum's intention is to try and get the real stuff as much as we can in front of you. So, for example, at the Perot Museum, we have, of course, a very large, beautiful skeletal mount of a sauropod dinosaur called Alamosaurus. And the entire skeleton is a cast skeleton. It's actually a 3D printed skeleton off of scans from 3 different institutions. We have the next series, so if you ever get to go to the exhibit, we have the real bones on the ground right in front of them, but it also has scans from bones in the UT Austin and the Smithsonian. Those are the other institutions that have chunks of Alamosaurus that we can then pull together into a skeleton. But one of the reasons why Alamosaurus in particular is entirely cast bone is because one of those vertebrae is solid rock. It weighs about a ton. So there's no way you could put those stuff up on display. You can't hang them from the ceiling. You can't hang, you can't even get like a wire or metal cup to set them in, because sometimes the material is just too heavy. So the majority of the skulls that you see in museums that are part of skeletons, they're almost always cast materials because skulls are incredibly heavy. Additionally, if that is the only specimen of that particular dinosaur, and it's so fragile, say like a skull of a T-Rex, you're not going to risk that particular specimen by putting it on display on a skeleton. So again, you make a cast copy of it, an exact copy of it, and then put that out on display. So answer is museums have a combination in all their skeletons of real material and cast material if they can. And if they can't put the real stuff out, they at least try and put something nearby, or they get you as close as they can to the real stuff.
Okay, so I am going to ask a question for, I think it's both of you. So the question is technically the fact that, like, dinosaurs are huge, right? I don't know if those are just the most popular ones or what, but they're huge. I assume that plants were also that big. And if so, why is the difference? And while y'all answer that, I'm going to disappear for just a second, but that is y'all's question. If y'all don't mind answering it, I'll be right back.
Wait, why is what's the question? Why is the difference?
So the question is dinosaurs are usually huge, which not really.
Not really, yeah.
Usually find.
Plants are huge
plants
too.
that big as well, and why was that? Why were they so big?
Oh, okay.
So do you want to take the plant side?
Sure. Okay, so yes, there are gigantic plants that grew very, very tall. And what's really kind of interesting is that to be really tall, to have a really tall trunk, you have to solve some of the structural challenges, right? So you have to have some kind of system to keep you vertical. So there has to be a lot of fiber in that trunk, and there has to be some kind of rooting structure. But way back in the day, like in the forests of the kinds of forests that produce the big coal deposits that we find where coal comes from, those big swamp forests, those trees were enormous, but the root structure wasn't the same kind of roots. They weren't like, they weren't botanically roots. They were really little extensions of the stem, and they were there to help to support those very tall trees. And in terms of their taxonomy and systematics, let's say in terms of who they're related to things that today are very small, which is really interesting, that's all that's left of those more primitive groups of plants. And today, the really big, tallest trees are either tropical forest flowering plants that grow up to, about 100 meters, so 300 feet tall.
Yeah.
In some of the tallest, wettest rainforests on Earth. And then, of course, the big sequoias. So, they can get really, really huge. And, of course, they can also get really, really tiny.
Yeah.
I think it's a matter...
You can find petrified tree logs, and I've, like, laid down next to them, where they are... I'm about 5'10". They are meters taller than I am. So you
many meters, yeah.
Find some of these ancient fossilized forests where you can just look at what's left, even part of the trunk, and they are so incredibly massive.
Yeah, they're massive. So you need to make those, to have those plants evolve into those. It's not only the structural requirements that can keep them upright, but also plants need sunlight, CO2, and water. And so if you can maximize the presence of those things all year round, you can then maximize the productivity, the net primary productivity it's called, or the plant matter that you can produce. Yeah.
Absolutely. I will say, as far as the vertebrate side of things, I mean, just off the bat, unfortunately, there is a bit of a bias in the fossil record towards larger things, because if you had a lot more hard, chunky parts to your body, you were more likely to fossilize. So it isn't exactly correct to say that we only have big things, because unfortunately that's really the only stuff we find most of the time. Now again, in these earlier, lagoonal situations or areas that have very quick and good deposition, we can get some of those smaller animals, and we find dinosaurs that are as tiny as a mouse. It's just, unfortunately, when you're that tiny and delicate, you're less likely to survive the forces that are ultimately trying to destroy your body and return you, to the earth. So I will just say that I think, though, the intent of the question was also to ask, why did dinosaurs get so big? And it is something that we do not, again, 100% understand. It's still being worked on. But honestly, it has to do with the plants. Dinosaurs were able to get big because there was an incredible abundance of material to consume. And if you, as an herbivore, had a veritable buffet right in front of you every day, because those plants are in such a good environment to grow and to grow rapidly and to grow big, keeping in mind during the Mesozoic, it was warmer. It was a hothouse world. There was evidence to suggest there were higher levels of CO2 and of O2, which are both things that plants need to grow and get big and strong. So you, as an herbivore, you were able to get big and strong if you had a lot to eat. And because you got big and strong and therefore could defend yourself more easily, your predators had to get big and strong as well. So it's just this constant evolutionary arms race that just kept pushing each other bigger and bigger and bigger, because one, the energy was there. There was enough consumable material to give you enough energy to get big. So it goes a little bit into trophic levels, it goes a little bit into other things, but I also want to point out that during mammal age, the Cenozoic, there were absolutely gigantic mammals as well. This is the giganticness of life was not just in dinosaur times. there were rhino-like mammals that got to be as tall as sauropods could be, Indricotheres. Even before...
Sorry, can you tell us what those words mean?
Indricotheres?
Indricotheres, you said as tall as something. I'm sorry.
Okay. A tall sauropod, so long-necked dinosaurs. So think like Brachiosaurus, right? The big, long-necked dinosaurs. Indricotheres are like a rhino-looking animal without the horn and on stilts, basically. Those things can get really huge as well. And even up until the end of the last ice age, 10,000 years ago, we had incredible amounts of megafauna, from mammoths to giant ground sloths to giant terror birds and everything like that. So I think, unfortunately, again, pop culture wise, we tend to only think of dinosaurs as big, sexy, scary animals, but in reality, mammals too have experienced gigantic sizes all throughout the millions of years that they've been dominant on this planet.
Okay, so we do have a bunch of children who are watching, so I think we probably want to try to wrap up around 9:30. If you don't mind, I'm going to go into the plant life a little bit. Hillary, obviously, you're always welcome to add input whenever you have something that
I love this. I learn a ton every time I talk with Bonnie myself, so I'm excited too.
That is perfect. So, Hillary, you talked about how studies are talking about like de-evolving chickens, where chickens to dinosaurs or dinosaurs to chickens, they help cancer studies today. So, Bonnie, is there a similar effect that paleobotany has that made in science? Besides the fact it's cool, we get the information, we understand climate and stuff, like, is there something equivalent like cancer research that we could get from this?
Oh, yeah, absolutely. So most of our medicines, actually a large proportion of the medicines that we consume come from plants originally. So they eventually get synthesized once it's figured out exactly what compounds are the active compounds that are having an impact on people. But medicines come from plants, So some of those are found by way of the cultures of indigenous peoples that rely upon their passed down knowledge of different plants having different impacts. So I guess one of the well-known ones would be salicylic acid, which is the active compound in willows that gave us aspirin. And so it was known that willows could help you if you had pain. I don't know how you prepared the willow, but people, I don't know, but people knew, and eventually it turned into, it became something that we produced in a big form as aspirin. We have, there's so many compounds. The compound that produced quinine, which was used to prevent malaria, and there are all kinds of, different generations of compounds that are used now to prevent malaria. But so and similarly with the chicken example, that genetic breakdown, that understanding at the gene level is something that is completely prevalent everywhere now in the biological sciences. So every plant species, practically not every plant species, but plant species now are being studied at the genetic level. And that helps botanists, neobotanists we would say instead of paleobotanists, neobotanists figure out the relationships among living plant species. And it tells you, that is the genetic distance, the difference genetically between species A and species B, might tell you that those two things are related because they share a certain amount of their genes, but their relationship goes way back, way far back. They split apart a long time ago because they only share a small number of genes in common. And so sorting out the genetic history or the evolutionary history of plants using their genes for modern plants is one of the things that neobotanists do, similar to looking at the chicken's genes and relating that back to fundamental aspects of their dinosaur history. But you can only test those ideas, right? You can only test those relationship ideas by going back to actual fossils and saying, well, okay, we think based on the modern genes that this plant A and plant B must have been originated, they split apart from each other in an evolutionary sense. We think that happened 60 million years ago or 40 million years ago. Well, but you can only test that by going back to the fossil record from 60 and 40 million years ago. Were those two things already existing, 30 million or 80 million? And so the plant fossil record, just like the fossil record of any life form, can tell you really what was around when and how these things are related to what we end up with here on Earth today. You know what I mean? Am I being clear enough about that? I'm not sure I am.
I think you are, but that really goes with one of the things that follows up. I know you're not quite done, but maybe you can
Oh yeah, that's good. Let's go with the follow up.
Yeah, so I guess I've mentioned it a couple of times, but I don't think it's actually been explained. But how can you tell the climate changes or climate of different time periods by looking at the plant fossils?
Oh yeah, okay. So there's a couple of different ways to do that. So what I often say to people is, if I showed you a cactus, right? Okay, we just know, just because we just know, right? The cactus lived in hot, dry places. That's what everybody would say. Everybody listening to this would say that, right?
Right.
So if you dig up a deposit and you see that you have fossils of cactus, you have fossils of succulents, and they're all growing together, and you then work with your geologist colleagues who are working on the same sediments, and they find evidence in the ancient soils that the soils were drying out. So you put those pieces together, and you say, okay, well, it's pretty likely that this was a hot, dry environment. So you can use your living modern day analogs of the fossils that you're finding to tell you about ancient climate. But there are other ways to do it as well. And one of those things that we use is the morphology, or the shapes and sizes of leaves, for example, to tell us about ancient climate. And so one of the kinds of studies that several people have done, including me, is that if you look at an assemblage of plants today, and the leaves are all really big, and they're kind of leathery, or they're of a certain size, even though all the different species that are co-occurring together, then you are statistically likely to be looking at something that is occurring where your assemblage occurred in a wet climate. Lots of rainfall, lots of available moisture. And that's because today, when you find species, even if you're in different parts of the world, even if you're looking at an assemblage of plants in the Amazon over here, and you're looking at an assemblage of plants over here in Southeast Asia, all those species are going to have leaves within a certain size range, because there's ample rainfall, there's ample sunlight, there's ample CO2. You're in a wet, warm climate. And so you're just using the morphology. You're not using who they are. You're just using what they look like. And that's because these plants have evolved to live in certain physical settings, and they've solved the problem of how best to grow in those settings. They've solved the problem in similar ways, even though they're not related to each other, right? They're plants, they're flowering plants, but they're not closely related. But they all have similar kinds of leaves. So that's another way of using plants to tell about ancient climate.
And I'll say, just for the Perot Museum, some of the research we've done, again, a lot of the research we've done is taking place up in Alaska. So a lot of people think of Alaska as Arctic tundra, you don't get a lot of plants there, but they're all evergreens and whatever. And there's evidence to suggest that there were palm trees in Alaska. So how could that possibly be? Palm trees, which are known for warm, wet, humid environments, possibly live up in Alaska? Well, it suggests that during the time of deposition, that during the late Cretaceous of Alaska, it was a much warmer and wetter place. And so we can understand, like Bonnie was saying, about what plants are found there and their leaf shape and everything. That can help us infer then, well, if palms are there, it must mean that it is was a warmer place millions of years ago.
Okay, so that actually it kind of answers this question, but I still want to ask it explicitly. So you know in the I don't remember which dinosaur movie, but they have the star leaf, right? Like I think it's
Leap Before Time.
Yeah, and so I don't know if that's true, but the main question is like, does it seem like trees have always had an autumn where they're going to be like dropping all these star leaves and stuff down?
Oh, that's such a great question. I love that. That's so awesome. Okay, so that would be like the equivalent of sweet gum. That's like a sweet gum, yeah, which we have in the South. But yeah, do they always, are they deciduous? That's what dropping your leaves is. The word for that is deciduous. So in cold climates, plants lose their leaves for the winter, right? Yeah. So in the tropical regions, the parts of the tropics where it's seasonally dry, plants lose their leaves because of the dry season. So if there is a stressor on plants where they then can't get enough water, and the reason in the cold place is because the water is frozen during the winter months, they cannot continue to photosynthesize properly because the water's frozen, and also they're in danger of having problems of freezing sap in their trunks, which would be a problem because when water freezes, it expands, and you don't want to ruin all your cells that suck up the water into the tree. So you shut down for the winter, and in the tropics you shut down for the dry season. And in both cases, plants will lose their leaves, and that's a good thing for paleobotanists because it means that leaves are falling down. And that's a great thing because then they get deposited and hopefully they get preserved and then we can find them later. But that in itself, if you can tell from your plant fossils if the plant was deciduous, that tells you something. It tells you that there's seasonal hardship that causes these plants to lose their leaves. So again, being deciduous it's solving a problem for the plant, the problem of a lack of water during part of the year. And so the solution is to drop leaves. And so that tells you something about climate too.
That's actually really cool. So I actually learned things about normal plants as well.
Cool.
Yeah. I just learned something too, so thank you.
I apologize to people asking questions. I don't remember who asked what. These were all phenomenal questions. I think I'm going to ask 2 or 3 more if y'all don't mind, and then we'll call it a night.
Okay.
These questions are all great, so I really feel bad calling it a night before we answer them. So I appreciate y'all, Bonnie and Hillary.
The conversation doesn't have to end. You can absolutely email or whatever. Please feel free to keep contacting.
Yeah. That's absolutely true. Yeah. So Hillary gave her info for social media. Bonnie, if people had questions specifically for you, could they just go to SMU's website and find you and message? All right. So that's all you have to do. If you want to find either one of these, Bonnie is at SMU or the Southern Methodist University. Hillary is
just B. Jacobs there. B. Jacobs at SMU.
Perfect.
Yeah.
And y'all can.
I mean, to be honest, if you don't remember my social media tags, you can also just email the Perot Museum, and they will kick questions my way. So don't hesitate.
That's perfect. But I do, like I said, I want to ask 2 or 3 more questions if y'all don't mind, and then we'll call it a night. So just stick with me if you don't mind. So one of the questions that have been asked. It's going to be circling back a little bit, talking about the dig sites and everything. So whenever you have the vertical plant trees, does that make things a little bit harder whenever you're doing like the dating, the carbon dating or whatever, or anything like checking the layers that you're finding your fossils? Could a tree mess that up because you have, like you said, like the 300 meters tall or whatever it was, like something ridiculous?
If they're up and down in the stratigraphic layer versus laying sideways?
Exactly, yep. Does that
mess you guys up?
What do you mean?
Down?
Well, I'm not quite sure.
So the exact question is, do vertical plant or tree fossils make things easier or harder to date since they're perpendicular to the geological layer? So oftentimes we do like geological dating of like, we can see that like this was this time period and then the next thing is sediment is different. Like, do trees ever get stuck in there and start messing stuff up?
Well, you can usually see, if that's the case, you can usually see what's going on there stratigraphically. So I've seen sites where you have preserved a forest essentially in situ, in place. So you can follow the horizon and you see tree stumps. There's a place in Ethiopia that was amazing where these trees were preserved in growth position. Sediments came subsequent, they got buried. So, you can see the burial of these trees that were in place, okay? And then when we came along millions of years later, these sediments are being eroded by modern day processes, and the trees are literally, the fossilized tree trunks are literally just falling out of the cliffside. So they're in place. Mm-hmm. The vertical nature of the tree is such that as the sediments erode away from them, they're just falling down. So you have to kind of piece back together the story of what happened first, what happened second. And when you get to the tree trunk, the stumps, when you're going down in terms of the tree's orientation, the layer in which they were rooted. I hope that
I think that
somehow. Yeah. If you're talking that's millions of years, and those are silicified trees. Okay, so those are turned to stone. When you're talking about radiocarbon dating, that's only for things that are organically preserved, because you're actually dating the carbon itself, right? So you have to have organically preserved material. You have to have carbon.
Actually, can you clarify that a little bit? Because I would have assumed that plant matter would be organic matter.
Well, if you're lucky, it is. But fossilized wood trees are not organically preserved usually. Usually they're replaced, and so they're what people call petrified wood, right? They're stone. So that stone doesn't have organic matter in it. And also different isotopes, oh gosh, this is getting complicated, but different radioactive elements.
Yeah.
So radioactive carbon is the isotope carbon-14, right? And that decays. So it has a decay rate that's a set decay rate, and you can sample your carbon. But the decay rate is such that you can't date anything with radiocarbon older than about 40,000 years. You can't go back millions of years with radiocarbon. Only it's only about 40,000 years because of its half-life is short.
Right? That's why a lot of archaeology and anthropology will use radiocarbon, but most paleontology, it's completely useless to us.
Right. But you can use other isotopes that have a longer half-life and that get preserved in, say, volcanic settings, right? So when volcanic material crystallizes out, those crystals contain other kinds of radioactive elements like argon. So argon-40, the isotope argon-40, it has a very long half-life. So you can go back millions of years and use argon-40, argon-39, which is the daughter product, and you can get a date that way. So going back to the trees, if you have your tree stumps there, and you have volcanic ash that's fallen down around your trees, right? That's happened pretty quickly. We're talking about millions of years, right? So that's happened really quickly after your trees died. Or maybe even the ash killed the trees. And then you can use your argon isotopes to tell you the date of that volcanic eruption that fell on top of the trees. And then you know how old your fossil trees are.
Yep, that's crazy. I've heard about carbon dating. I guess everyone has, right? That's always
usually what people think of. Yeah, right. So there's all different isotopes that are used for. There's also uranium.
Yep, uranium is what's used a lot time in vert paleo. Is uranium.
Uranium, lead, but you can have bones preserved in Africa because the Rift Valley is such a volcanically active region, or in other volcanically active regions. You get bones preserved sandwiched between volcanic layers, and they're dated that way
volcanic ash layers are awesome because sometimes you can date them so specifically that you can get an incredible amount of decimal points on that specific date versus a general range of dates. So volcanic ash is awesome.
Yeah.
All right, I am terribly sorry. I'm going to ask one more question. It's going to be the last one. We have so many from everyone. So if you look in the chat, Jackie Baeza has actually put the contact information for both of our speakers here tonight. So if you do want to follow up on any questions, please reach out to them. They'll be happy to get back to you when they can. So the last question I want to ask is again for Bonnie, but again, I want to hear both. So actually it's about fungi. So how well are fungi preserved in the fossil record, and would that count towards botany as well?
That's a great question. That makes me laugh because, yeah, so back in the old days meaning like in the Victorian era, people who studied plants would also study fungi. But you know, it's since genetic work has been done, it's become known that a fungus is actually its own thing, right? It's its own phylum, it's its own group completely. And actually, genetically speaking, it's closer to an animal than it is to a plant. So a fungus, yeah, right? Isn't that crazy? And
so cool.
You know, fungi do their crazy things. They you know, just like a fungus would get on your feet and start eating away at your skin. Well, you know, fungi send out these hyphae, and the hyphae can get on things and decompose them like outside their bodies and all kinds of things like that. So if you want to have a monster movie, you know, you just use fungus. That would be like the best sci-fi ever. Yes, I always say that. You know, like I want to see the
first, folks.
Yeah, I want to exactly. I want to see that monster movie that uses a fungus. Right. So technically speaking, you know, biologically speaking, it's not really considered paleobotany. But of course, there's a close correspondence, and there's a similar way of preservation, and there are such close relationships between fungi and plants that you sometimes find them together. So we find fossil leaves that have fungus growing on them. Right, so plants have to be wary of getting what's called epiphyllous fungi on the leaves, and then they do harm to them. So that's not a good thing. And there are also, you know, a fungus that are they're symbiotic with plants in their roots, and so the fungus. They send out their hyphae, and they provide nutrients to plant roots and to the plant then. And the roots provide carbohydrates, the products of photosynthesis, in return. So it's a very tight relationship. It's a symbiosis. It's a very tight relationship. And that goes back. There are fossils of roots containing fungi in a symbiotic relationship that goes back 400 million years, which is amazing.
Bonnie, and I'll just real quick, is this true or not? Because I think I heard this, that the first organism to actually make it up onto land, even before like herbaceous plants, was like giant mushrooms or giant fungus or something. Or am I wrong?
No, it's not that you're wrong. It was published as such.
Okay.
I think there's still some question as to whether that was really a fungus.
Okay.
Yeah, that's that big thing. Yeah, I know what you're talking about. Yeah.
So something to do some research into, folks.
Yeah.
All right, so I am going to stop the answering here. I want to do a couple of shout outs if y'all don't mind before we sign off. So like I said earlier, Tap Talks literally could not be done with an entire team of people. This is our 2-year anniversary, and there's no way I have time to shout out to everybody who has helped make this a thing. Not only do we have our speakers, we have all the participants who come and actually make this worth our while, that you come and you ask us questions, you make us think about things that we hadn't even thought of before. But specifically, whenever we had to move to virtual, someone I really want to make a shout out to is Benjamin Smithers. So Ben, if you don't mind turning on your camera, so just so you all know, he's been here this entire time. He makes sure that all our tech works. He's the one who streams it. He makes sure that our sound is working. You'll have no idea how much work he does behind the scenes. And I want to make sure he does get the shout out. If I did not have Ben, we literally would not be doing this. Like, I literally, there's just no way. every time we were like, can we do this? He somehow manages to make it a real thing. And so I do want to make sure Ben is acknowledged for this. We got to the 2-year mark. We wouldn't have made it if we hadn't been able to move to virtual. Couldn't have made it without our speakers. There's a few other people. I don't have them on this channel because they're not doing the tech parts as, per se. But Jackie Baeza Rubio, she is our PR director. She's the one who makes sure the word gets out to all of you. She's the one who does all our social media. She's the one who makes sure things actually make sense, that we are putting the right information out there. We absolutely need everybody who's on this team. Like I said, I can't shout out to everybody. Whenever we were doing it in person for the past year, we had Logan Norman who did all our stage setup. We had Symmetra Pingokar who would actually make sure that I had the information I needed before I went on stage, who made sure that the trivia answers were graded. Actually, trivia, good point. Ben is also the one who puts together a trivia. So I gave him the shout out for all of the technology. He's also the one who helps come up with the trivia questions and answers. We also have Nick Burns, who whenever we were doing virtually was also the director of scientific inquiry. And so he also helped doing all the trivia. We had this huge team, this wonderful amount of people. We have sponsors. We have UT Arlington who made sure that we could have all the equipment we needed in order to do our in-person events. We, again, as soon as we can, when we feel as scientists it is safe to be in person at Brewers again, we will go back to being in person. We will use all these sponsorships again. We've had tickets to different museums donated. We have the speakers like Hillary at the Perot. We had tickets to the Fort Worth Museum of Science. We had a speaker from the Amon Carter Museum. We have had such wonderful support from all the different DFW locations. If any of you have requests or suggestions for other speakers or topics or locations we can reach out to, please give it to us. That's how we're going to make it to a 3rd year, is we need the input from everybody. So thank you absolutely everyone on the team, to our speakers, and to our followers as well. And again, if you like what we're doing, if you'll hit subscribe, that's underneath our YouTube video, you should get a notification next time we go live. We're not sure what our next topic's going to be, but we'll have it in a month or 2. We'll post it. So thank you, everybody, and hopefully I'll see you at our next talk.
Bye, everyone.
Thank you. That was fun.
Bye.
Bye.
Ben, are we done yet? Now's the awkward part where you'll have to wait a moment.